Sometimes you have data that is not continuous but discrete in the form of integers. By the way, watch it. The spelling in discrete in this case is ETE, meaning integers, as opposed to EET, which means, shh, let's keep a secret. Well, it turns out you don't use regular statistics for continuous data, like measuring dollars or inches of rainfall, where you can have actually decimal points. But on the other hand, for things you count, they're always integers. Now, the mathematics, while it looks a little daunting, it's really very simple. We academics just love our notation. You don't have to know the notation. And well, it turns out you're going to have say, M by N row and column. Let's call it a matrix. And it turns out we're going to keep track of the number of cells, and we're going to label that a degree of freedom. And they call it that because, once you have all the cells assigned, well, you always know that that last one is the remainder, and so therefore we're going to subtract that last one, the remainder. So the degrees of freedom is the rows times the columns minus 1. And what we're going to do is figure out what would be a likely distribution if the chances of being in each one of those cells was equal. Well, they may not be equal because there may be more in one row or more in one column, so we're going to take a weighting of both the rows and the columns, and of course the weightings add to 1. Then we're going to compare that with the original data, figure out the differences, and square them, divide by what we would have expected, and we add them all up and we get a figure. It's called a chi-square. And you know what? We're going to go to a table, and bam! It's going to tell us whether it's too random, too even, or somewhere in between. Now look at this for a second, or maybe it's a New York minute, and you'll actually note this is really not a surprise. What did we do with the variance? We took the actual case minus the mean, squared it, divided by the number of cases. Then, of course, took the square root for the standard deviation. Look how similar this is here. We took the actual case, the observed, minus the expected, which, of course, is what? The mean, squared it, and divided by the number of cases, which here it would be the expected. Very similar to the statistics we've already looked at. Okay, here's our computational example. It can easily be done by hand. Did it on a spreadsheet. And we have, let's say, 3 classes with either females, or maybe they're finance majors, and males, or maybe they're marketing majors. And in Class A, we had 6 and 14, respectively, 8 and 12, respectively, and 14 and 26, respectively. And the total number of female finance majors added to 28, and the total of the male marketing majors added to 52. There was a grand total of 80. And looking at it row by row, class by class, we had 20 in Class A, 20 in Class B, and 40 in Class C, and of course, again, added to 80. Now, what we're going to do is figure out some weightings. And we're going to take the proportions of the rows and the column totals of the grand total, here 80, and it turns out we have, a quarter in Class A, a quarter in Class B, 1/2 in Class C, and of course the weights add to 1. With respect to the columns, the type of major, if you will, we will take the 28 versus the 80, and 52 versus the 80, and in fractional form, it would be 7/20 and 13/20, which still add to 1. Moving on to the second of our 5 tableaus here, we're going to take each of those weights, horizontal and vertical, multiply them times each other. And sure enough, we've got them in there. Let's see, we got a 0.08 and something, and a 0.16 and something, repeats for B, and 0.17 and something, and 0.32 for C. And of course, they still add to 1. Now we take those weights times the grand total of 80, and we get for classes both A and B 7 and 13 respectively, and for class C we get 14 and 26, and you add them all up and you get again 80. And what we're going to do is move on to the fourth tableau, wherein we take the differences from what we would expect, that was our tableau number 3 we just created, compared to the original data. And sure enough, in Class A, there was one more and one less of a student type. But likewise, in Class B, that was true, but it was reversed. So the differences are -1 and +1, and likewise +1 and -1. Class C was no difference. Now, what we're going to do is square them. And at this stage, notice that the differences will always add to 0 in both columns and rows. And if you remember, we did the same thing in our variance computation, where before squaring them, the differences always added to 0. Before we go to our final step looking at that fifth tableau, let's do a bit of a refresher. We realize there are m by n number of columns and rows. That means there's a total of m by n cases, and we're going to subtract 1 for the degrees of freedom. Why? Because the last one will always be determined if we know the total. And we're going to create some weightings on the sides and on the bottom, and those always add to 1. When you multiply them times each other, they still add to 1, and we use that to compute what we would expect for each one of the cells. We're going to take the difference from each cell, here the observed minus the expected. Now we're going to square them and divide by what we would have expected and add all of that up. Well, back to our final tableau. We're going to square what we had in the fourth tableau, divide by what we would expect in tableau number 3, and there's the computations there. 0.14, 0.07, 0.14, 0.07, positive numbers, and zeros. Add them all up and we get 0.439 and some change. And what we're going to do now is go to a table. But before we do, let's look at what I've put on the right-hand side, where all I did is rearrange classes A and B at the very top, where I increased and decreased 1 between the two types of students, where the 6 became a 7, the 14 became a 13. In Class B, the 8 became a 7, the 12 became a 13. And look at that. Everything looks the same in tableau number 2, as you'd expect, and likewise tableau number 3. And notice that between tableaus 1 and 3, there's no difference, meaning this is exactly what you would expect. And the differences all add to 0. Squaring them, adding them up, you get a chi-square of 0. Let me pause at this stage that some of you may have heard of Mendel with his peas that were wrinkled and not wrinkled. Well, it turns out, the things about genetics, 1/4 of them should have been wrinkled, 3/4 should not have been. And so he did his tables, and you got distributions that look like 3/4 and 1/4. His assistant made the numbers too nice. He made them fall closer to what you would expect between 1/4 and 3/4. And as we will see with some better statistics now, it was too nice. So let's look at the results. And we do that by going to a chi-square table. Now we're going to go on the fifth row, y, rows times columns, -1, degrees of freedoms, etc. And we look across for the value we just calculated. And it turns out, look, it's on the far left-hand side. And it's associated with a 0.99 that it's saying it's really a little bit too nice. It's too evenly distributed, which may or may not be good. But if it was random, you'd expect something a little bit more noisy. So with that in mind, let's go to some other examples. Here I've got 2 more scenarios. On the left-hand side, I've massaged the data just a little bit. On the right-hand side, I really moved them around. And let's see, we got 10 and 10 cases for A, 4 and 16, 22 and 18. And you work it through all the way to the bottom, and we get a chi-square of about 6.8 and something. Now, on the right-hand side, I really moved them around, and especially in the case of Class C, where I made it 30 and 10 respectively. And notice again, in both of these, they still added to 80. The column and row totals always were the same. Therefore, our second tableau, the weightings were the same, but the expectations started to become different. And look, if we really have extreme data, because everything is very different between each class, we get a larger chi-square. So again, let's go back to that table. So we take that value of 6.8, and it kind of falls right in the middle. It's above the 1.6. It's below the 9.2. It's kind of like Goldilocks and the Three Bears. Don't get me started. So it's kind of in the middle. It's kind of random. It's kind of the noise we would expect. Now, that value of 16, look at that. It's on the right-hand side beyond our last value. It's at the 0.01 level of saying this is not what you would expect. It is not random. And it's not random in the sense that it is extremely differentiated. Comparing that to our very first one, it's not random, but it's not random in the sense it's too nice, it's too even. Well, let's summarize. In our first scenario, which if you recall, we only changed one student from one class to another class in terms of type, and we got a 0.439er versus the table value of 0.55, and it was at the 99% level that it was just too even. That last extreme scenario where we had 16.5, the right-hand value on the table was 15.08, and it was at the 0.01 level that it was too uneven, that it was not random. Then we had something that fell in between of 6.86, and we noted that it's kind of, that's what you would expect if it was random, with Dr. C doing chi-square. Oh, by the way, if you were wondering why that song I selected at the front, which is usually thematic, the reference was Don't Be L7. L7 used to be jive talk for L7 made a square with your hip, Dr. C.